Today, we're going to dive into something that honestly sounds like it's straight out of science fiction, but it's very real and it's changing the game for data privacy. We're talking about homomorphic encryption. It's this incredible way to work with data while it stays completely secret. So, let's break down how it all works.
Okay, just think about this for a second. What if you could take your most sensitive information? We're talking medical records, financial data, you name it, send it up to a cloud server to run some really complex analysis and get the answer back, all without that server ever getting a peek at your actual data. That's not a trick question. That's the core promise of homomorphic encryption. And this is really where you see the huge difference. With traditional encryption, if you want to actually use the data, you have to decrypt it first. And in that moment, it's exposed, it's vulnerable. But with homomorphic encryption, well, the lock never comes off. The data stays secure, private, and encrypted through the entire process.
So, that's the big promise, right? Total privacy, even while your data is being processed. But the immediate question is, how on earth is that even possible? So, let's take a look under the hood and get a feel for the mechanics. And just so we're all on the same page here, we're not going to get bogged down in the super heavy mathematics. The whole point of this is to build an intuition for the brilliant ideas that make this technology tick.
The workflow itself is actually pretty elegant and simple. First, you take your regular data, the plain text, and you encrypt it. That gives you this ciphertext. Step 2, and this is the magic part, you send that ciphertext to a server, and it performs all the computations directly on the encrypted data. Then, step 3, you get the encrypted result back, and only you, with your secret key, can decrypt it to see the final answer. The server in the middle, it never sees a thing.
Okay, so that process sounds simple enough, but making that second step happen, the whole computing on secrets part, that takes some seriously clever mathematical building blocks. So let's dig into how it's possible. So here's the first key insight. The data isn't just randomly scrambled. The first thing that happens is it's encoded into a very specific mathematical structure, a polynomial. Now, this is absolutely crucial. By turning our data into this mathematical language, we can suddenly perform operations like addition and multiplication, even on the encrypted version.
And you might be asking, well, is this actually secure? The short answer is yes, it's incredibly robust. The security is built on top of what we call lattice-based cryptography. All you really need to know is that the math problems it relies on are understood to be exceptionally hard to break. We're talking hard even for future quantum computers. That's what gives us real confidence in the security of these systems.
Now, as with most things in engineering and cryptography, this amazing capability doesn't exactly come for free. There's an inherent trade-off, a challenge that had to be solved to make this all practical. And it all comes down to something we call noise. So think of it like this. Every single time you perform a calculation on the encrypted data, every addition, every multiplication, a tiny bit of mathematical static or noise gets added into the mix. It's just a natural side effect of how these operations work on encrypted data.
And here's why that matters. If you perform too many operations, that noise just keeps building up and up and up. After a certain point, it gets so loud that it completely drowns out the original signal. When you try to decrypt the result, you don't get your answer, you just get junk. For a long time, this was a huge roadblock, limiting homomorphic encryption to only a few simple calculations. So, how do we get around that noise limit? Well, the solution is what took homomorphic encryption from being this fascinating theoretical idea and turned it into a practical, usable tool. It is a truly brilliant breakthrough.
The solution is a procedure called bootstrapping. You can think of it like a cryptographic cleaning cycle, or a reset button for the noise. It takes a noisy, well-used piece of ciphertext and, without ever decrypting it, runs it through a process that spits out a fresh, clean ciphertext. It has the exact same data inside, but the noise has been reset back to a clean, manageable level.
And the impact of this is just a total game changer. By being able to periodically clean the ciphertext and get rid of that accumulated noise, we effectively remove the limit on how many computations we can do. This is what finally unlocked the ability to run really complex, deep algorithms on encrypted data, which was the whole point from the very beginning.
Okay, so let's just take a step back for a second. We've gone through the core mechanics, right? The polynomial encoding, the challenge of noise, and that elegant solution of bootstrapping. Now let's just pull it all together for the big picture and recap the key takeaways.
So when you boil it all down, here's what we've got. The flow is simple. You encrypt your data, it gets computed on, and then you decrypt the result. The method that makes this possible is encoding the data as polynomials.
The security that holds it all together is based on really hard lattice problems. The one big hurdle is that every operation creates noise, but the brilliant solution to that problem is bootstrapping, which cleans the noise and lets us keep going.
So understanding these fundamentals gives you a really solid foundation for what this technology is all about. But the story definitely doesn't stop here. The real world gets even more interesting, because there isn't just one way to do this. There are different schemes, each with its own trade-offs, which sets us up for a much deeper dive into this incredible field.